Good day. Welcome to the Physics Exercises channel. Today I will be solving a problem known as the moving wedge problem. So the moving wedge problem reads as follows. We have a wedge with mass capital M resting on a frictionless horizontal tabletop. Okay, so here's the tabletop, and here's the wedge. A block with mass M here, small m that is placed on the wedge. There's no friction between the block and the wedge, and the system is released from rest. Now we are to calculate the acceleration of the wedge and actually the acceleration of the block, which has horizontal and vertical components. Okay, and then we play with the limit when m is very large. Okay, and we try to assess the shape of the trajectory of the block. Okay, now the interesting part of this problem, let me erase my arrows because I will use that. This figure some more. So the interesting part of the problem is that the way I'm going to present the solution, I will make use of what is called a non-inertial reference frame. Sorry, let me start that again. Non-inertial reference frame. Okay, so that's the PHYS here. Sorry, that should be an A, not an E. Okay, so we're going to use this technique to solve this problem. Okay, and what a non-inertial reference frame is, as opposed to an inertial one, that's an R, and that's an N, okay, is one which accelerates compared to an inertial reference frame. Okay, and I just outlined that when this technique is used, when you solve a problem using a non-inertial reference frame, what you want to do to make it useful and be able to apply the modified versions of Newton's laws in the non-inertial reference frame is to offset the acceleration of the reference frame by a fictitious force. But more on this as we solve the problem. Okay, so the first thing I will do to start the solution is to draw the free body diagrams. Okay, and we have two objects. Let me designate those objects by their masses. Okay, and if you take the block, which is small m, okay, the block is here, okay, and that has two forces acting on it. If you inspect, one is, of course, gravity, and there's a contact force between the block and the wedge, and that contact force is acting that way. I'm going to call it F. So F is the contact force between the block and the wedge. Okay? Okay, now let's keep going. There's another free body diagram to consider, and that free body diagram is that of the wedge. Okay? And for sure, the wedge has gravity acting downwards. It is on a horizontal tabletop, or horizontal surface, which means that it will have a normal force acting upwards. And we also have, by Newton's third law, the contact force, an equal and opposite force to the contact force acting in that direction. Okay, let me make a little bit of notes here. Okay, I will make that in with, let's say, thinner and a different color. Okay, so let's say maybe blue. This is angle alpha. Okay, here you could say that's angle alpha, but you could also say that that's angle alpha. And, well, This is angle alpha. This is angle alpha. So I'm just filling in with the geometry because we're going to need that shortly. Okay, now go back to black, as Amy Winehouse would have said. Okay, now we want to write the equations of motion of these objects. Okay, and I guess I'll start with the wedge. It looks simpler. Moreover, for the block, I'm going to use a tilted coordinate system. Okay, we know we have experience with wedge problems, and we know that when we solve in a coordinate system which is tilted according to the wedge, then one of the equations of motion becomes easier, and I want to exploit that. Okay, and in the meantime, like I said, I will introduce the non-inertial reference frame too. Okay, so next step, let us go and calculate our equations of motion. Okay, so on the one hand, if you go to M, and I'm going to here use this coordinate system. Okay, so vertical and horizontal. Okay, and in the horizontal direction, you have that minus F sine alpha is equal to M times A. And by A, that's an unknown that I just introduced, but it's the unknown, one of the unknowns that we are looking for. So that's the acceleration of M. Okay, and this is minus actually, sorry. Okay. I set both of these to minus. In other words, the equation you could also write as F sine alpha equals MA. This will give me the absolute value of the acceleration, but we should keep in mind, looking at this picture, that this object will accelerate that way. Okay, so M will accelerate to the left. Okay, so let me just write that here in parentheses, because that's important information. So that's one equation of motion. We have another one which we're not really going to use, but I'm going to write it anyway. So we have the normal force minus the vertical component of the contact force minus mg, and that's equal to 0. Okay, we're not going to need this for anything, but we do have to keep this one in mind. Okay, and now we go to the block. Okay, and now for the block, I'm going to use the fictitious force. And for the fictitious force, I'll change color. Okay, so I will use a fictitious force. And why am I using the fictitious force? Because I'm going to switch to a non-inertial reference frame, as I said earlier. I want to be able to use the x prime, y prime coordinate system that I designated here. And in order to be able to do that, well, that's an accelerating reference frame, right? The wedge itself here is accelerating. It is accelerating to the left, okay? So we need a fictitious force to the right. Now, what am I going to call my fictitious force? Well, small f is already taken. So I'm going to say capital F is my fictitious force, okay? And so we have a fictitious force F acting this way. And it's in red because it's fictitious. And it has to offset the acceleration to the left, okay? It's acting to the right. How does it offset the acceleration to the of capital A to the left? If it acts to the right, and it's minus m times A, okay? It's not a real force. It's fictitious. Let me actually just, let me put a tilde on top. to indicate that it's somehow different. I feel a little bit strange using the F for force here because it's fictitious, and force is F is usually the variable that we use for force. Okay, so but let me actually emphasize here also that this fictitious force has to be of magnitude m times a. Okay, now let me summarize the steps here. I went over to a non-inertial reference frame. I'm going to do my calculation there, okay? But then when I go back to my, you don't want to report your result in a non-inertial reference frame, okay? You want to report the result in the reference frame of, for example, this guy standing here, okay? So right now you're solving your problem in this non-inertial reference frame, but then you have to go back to the inertial reference frame of this guy, actually. Okay, that's what the question refers to. Okay, so now having said this, let me remind us. So I'm going to remind us of the free body diagram. I made a mark here, which I didn't want. So our free body diagram for the block is mg, small f, and let's again go to red to do a fictitious force. F equals ma. Okay, and based on this, we can draw, we can write equations of motion in the coordinate system, which is specified by y prime x prime, which is the moving coordinate system or accelerating coordinate system. Okay, so we're going to take this as a direction and this x prime as a direction. So let's start with x prime. Okay, well, if I look at this, let me actually now switch to so basically mg has a component. So if I break this to two components, one would be this one and the other would be that one, and we know that this here is alpha. Okay, so one component going downwards, going in the x prime direction, is m. Sorry, let me go back to my usual thickness, usual line thickness. So we have mg sine alpha. Okay, so that's one force. We also have another force, and if we consider the geometry here, so here's the x prime direction, and this here is also alpha. So this is also alpha, an angle alpha. And then we can say plus f times cosine alpha. Okay, and we can then also say f tilde rather. Sorry, I made a mistake because I introduced a tilde and I forgot about denoting these tildes. So let me go back. There should be a tilde there, and there should be a tilde on this one. And in the equation, I'm not using the color red. Okay, I only use the color red on the free body diagram. Be careful with that. Okay, now what is this equal to? This is actually equal to m a prime, and a prime is the acceleration of the block in the non-inertial reference frame. Okay, and it's pointing that way. Okay, it's pointing in the x prime direction. We continue, and now we write the equations of motion in the y prime direction. In the y prime direction, you have F pointing upwards. You have the fictitious force. More precisely, its component, which points upwards, which is F sine alpha. Sorry. Sine alpha minus mg cosine alpha. And this is equal to 0 because in the y prime direction, we are not accelerating. Okay. And now, well, we have to count our unknowns. Okay, so we have actually 4 equations, right? But like I said, we don't need one. Anyway, we have 4 equations. So I'm going to count how many equations and how many unknowns we have. Okay, so let's go here and count the unknowns. Okay, so F is an unknown. Capital A is an unknown. I mean, I introduced that. And A prime is an unknown, and N is an unknown. Okay, but we don't really care about N. Okay, so we're not going to need this. But what I'm going to now do is to start putting the equations together to solve for the unknowns. Okay, so solve for the different unknowns. And since we are, one of the questions asks for A, what I'm first going to do is eliminate capital F. Okay, so from this equation up here, I can say that capital F is ma divided by sine alpha. Okay, and then I can make that substitution in here. But simultaneously, as I make this substitution, I'm also going to substitute for F tilde from here. Okay, and then I get one equation for A. So I can write, first of all, ma divided by sine alpha, that's this F here, okay, plus small m A sine alpha minus mg cosine alpha equals 0. Okay, so that's an equation which I obtained from this one. Okay, by substitution. And now I'm going to have m plus m sine squared alpha times A is equal to mg sine alpha cosine alpha. That's just the algebra. I multiplied by sine alpha and I made some rearrangements. And voila, we get that the acceleration of the wedge is mg sine alpha cosine alpha divided by capital M plus m sine squared alpha. Okay, and that's actually our first result because that's what the problem, one of the things the problem asks to calculate. Okay, so we have now that, and we have to keep in mind though that this, okay, if you want to go back and be very precise about the coordinate systems, this is actually a, well, it's to the left, okay? But if you're in a coordinate system which is like this, then it's a in that case would be negative. Okay, so be careful with that. Okay, our next part is, well, we still have one equation, okay? Because what happened now is, okay, I said that we're not going to worry about n, so we have one less equation, and n only appears in this equation. We just discard it and forget about it. We used this equation, and we made a substitution into the y prime equation, and that actually gave us the acceleration of the wedge. Okay, so now we have the acceleration of the wedge, okay, and we're going to use that to substitute into this x prime equation here, okay, because this has, of course, and we're going to solve for a prime, okay, so that's our next step. this F tilde is M, small m times A, and we have A. Okay, so what we need to do is, okay, first I'm going to rewrite the equation to remind us. This X prime equation has the form mg sine alpha. Sorry, I have to copy, plus F tilde cosine alpha plus F tilde cosine alpha equals small m A prime. Okay, but first, okay, so I'm going step by step here. mg sine alpha plus m times capital A cosine alpha is equal to m times A prime. I just made a substitution. Remember, F tilde was defined here like this. F tilde was m times capital A. Okay, and going further, but first of all, we can cross out all the m's here. Okay, and what we have, so we actually have the result for A prime if you want. G sine alpha plus capital A cosine alpha. But for capital A, I will substitute our already known result, namely mg sine alpha cosine alpha, but there's another cosine. So there's one cosine alpha coming from here and one coming from here. So that should be cosine squared alpha. And we divide it by m plus m sine squared alpha. Okay, and we don't want to leave it in this form. We're going to now say that, continue and say capital M plus m sine squared alpha, g sine alpha. Sorry, let me fix my, so that's an n. That's divided by m plus m sine squared alpha plus mg cosine squared alpha sine alpha. Okay, and if you inspect this a little bit, you see that we have a small m sine squared alpha g sine alpha and a small m cosine squared alpha g sine alpha. So we can simplify that and say we have mg sine alpha, that's this term, plus capital mg sine alpha divided by capital M plus m sine squared alpha. Okay, and you can simplify that further, of course, by saying that the total mass g sine alpha divided by capital M plus m sine squared alpha. But, so that's a number, okay? So that's nice, but you don't want to leave it in this form. And so there's two things that you still have to do with this answer. So remember that this acceleration is that way, okay? And it's in the non-inertial reference frame. Okay, so the first thing we do is, okay, so keep in mind that this here is our angle alpha, or this here is our angle alpha. And we will say that we will rotate it back to a reference frame. And I'm going to call this reference frame y prime prime and x prime prime. Okay? So we're going, this is actually the reference frame, which accelerates with the block, but is in horizontal and vertical components. Okay, so that's this particular reference frame. So this is actually accelerating with the block. Let me indicate that in red again, or in another color. So this is a non-inertial but horizontal. So this is still accelerating with the block that way. Okay. Okay, and if I do that, well, if I look at this and I do the trigonometry, I see that ax prime prime, you know what, I'll call this, it's nicer if I put the prime prime up here. Okay, so ax prime prime is equal to a prime cosine alpha, I think. Yeah. M plus capital M G sine alpha cosine alpha. And we divide it by M plus M sine squared alpha. Okay, so all I did is I multiply A prime by cosine alpha. And then I also have AY prime prime, which is actually minus M plus M G sine squared alpha divided by M plus M sine squared alpha. And then only at this point, I can offset the acceleration. Okay. So this acceleration, we have to subtract from it the acceleration A that we already calculated. So this A that we already calculated. Okay, and that gives us the acceleration in the in the inertial reference frame, sorry, in the inertial reference frame. Okay, so mg sine alpha cosine alpha divided by capital M plus M sine squared alpha. So our actual AX is AX prime prime minus mg sine alpha cosine alpha divided by M plus M sine squared alpha. Okay, and it's obvious that that gives us AX, that gives us, it just cancels this term, right, with the small m. Okay, let me actually just double check that if I did that right. Capital A, I'm checking that again, mg sine alpha, so small mg sine alpha cosine alpha per capital M plus M sine squared alpha. So yes, indeed, that's the term that gets canceled. So in other words, our final result for AX is mg sine alpha cosine alpha divided by capital M plus M sine squared alpha. At the same time, our AY remains the same. Okay, because there is no fictitious force in the Y direction. It was only in the X direction. So for this one, we will have to write minus M plus M G sine squared alpha divided by M plus M sine squared alpha. Okay. Okay, so that's actually so our answers to this question, the hard part of this question are the two accelerations. One is this, okay, one is this, and the other one is capital A acceleration, okay, which I lost, but it's here. Okay, so let me write that down. So those are the final answers. Okay, so A is, and actually now I will put a minus sign, okay? And I will explain why I put a minus sign. M plus M sine squared alpha, okay? So let me draw what these answers mean, okay? So if I go to my wedge, which is on a surface, and my block, the wedge is accelerating with acceleration A that way. And actually, this object accelerates with some acceleration, which is kind of that way, actually, okay? Because you have to take into account that the block M is, so small m is the block, capital M is the wedge. You kind of have to take into account that the block is accelerating, okay? This is the block, okay? So that actually, okay, you can guess the trajectory of the block. The wedge just accelerates to the left. That's an easy trajectory. But the block is not too hard either, because this is a constant. Okay, so this is a constant acceleration. All the terms here, alpha, m, g, capital M, small m, etc., that's it actually, are constant. So you have a constant acceleration in a slightly tilted direction. Okay, so that's what's going on with the block. And there was one more question, which is to take the limit when the block becomes heavy. The wedge becomes heavy, rather. Okay, so if the wedge becomes heavy, what happens? Okay, first of all, I'm going to say that m is much, much bigger than small m, and a tends to 0 in that case. That's nice. And what happens to the block? Okay, so if we go here, what happens to the block? Actually, as m becomes much, much bigger than small m, ax becomes g sine alpha cosine alpha. G sine alpha cosine alpha. Sorry, that was not very successful, so I'm going to redo it. And let me move the screen a little bit. Okay, so g sine alpha cosine alpha. What happens with ay? Well, if I look at this m dominates here, and this m dominates here. So in other words, what's going to happen is I'm going to get a minus, okay, g sine squared alpha. Okay, and this should be the same as the solution for the wedge when it's stationary. Okay, so if I have a stationary wedge solution, let's try that. Okay, so here's my m. Here I have alpha, okay, and this is m. Let's call it m equals infinity. So it's a very, very heavy wedge, okay? And then all you need is the gravity acting on the block and the contact force, which is, well, we could also call it normal force, okay? And in this case, the equations, well, once again, you may want to solve the equations of motion in such a coordinate system first, okay? And what does that give you if you solve it in this particular coordinate system? And let me call this y prime and x prime for the time being. And we see that the x prime equation is, well, if I separate mg into components, I know that there's an alpha angle there, okay? And so basically you're going to have that mg sine alpha is equal to m times a prime, okay? And then, so this means that your a prime acceleration is g sine alpha. And if you take its components, i.e. you go back to this reference frame. Actually, okay, I could have used simpler notation, but if you take your a prime, which is that way, and you separate into x and y components, you actually get that ax is, so if this is alpha, this again is an alpha, is g sine alpha cosine alpha, and ay is indeed minus g sine squared alpha. Okay, yeah. The other equation of motion that I didn't use here, but is the y prime, but let's just, okay, just to make everything complete, we see that the normal force has to be mg cosine alpha, okay, because f minus mg cosine alpha equals 0, no acceleration in the y prime direction. Okay, but that completes the problem, because if we go back here, this is indeed what we got for our accelerations. So this gives us a sense of confidence that we did something right here. that in the limit of large wedge mass, we do get the expected acceleration for the block. Thank you very much.